Welcome everyone. Today we're going to be evaluating a classic improper integral, the integral of x over 1 plus x to the fourth from 0 to infinity. And you may be surprised, or probably not surprised, that the answer involves our favorite constant, pi. So I don't think I should say too much, let us get right into it. We're going to solve this integral by first finding the antiderivative of the function and then applying our bounds. And we're going to find the antiderivative by trying to make a substitution. So your first idea for a substitution may be for something like x to the fourth, or the entire denominator, even a 1 plus x to the fourth. But if you try that out, you'll find that you're not really making the integral much easier to solve. So here we have to notice something. Notice how in our numerator, the term is x is linear. It has its polynomial of degree 1. So we want to consider when we make a substitution so that our differential of the substitution is also linear, because then the numerator will cancel out when we apply our substitution. And that precisely happens when we make a substitution of x squared. So let some new function of x, u, be equal to x squared. Then to make a substitution, we have to find its differential, which is going to simply be 2x dx by the power rule. And so dx right here will be du over 2x. And notice what happens now we have our new integral. If we make our substitution, the numerator stays the same. In the denominator, we have 1 plus x to the fourth. If u is x squared, then x to the fourth is simply u squared. And dx is equal to du over 2x. And this is what I was talking about. Notice when we made our differential, now here we have an x, and here we also have an x, so they will cancel out if we simply factor it like this. We have an x multiplied by 1 here, and also an x multiplied by 2, and then also with 1 plus u squared in here as well, and it will be in the differential u. And so these x's are simply removed, and we can simply solve an integral in terms of u, which will be 1 over, seems like 2 times 1 plus u squared. Why am I not opening this bracket yet? Because we can make the integral of 1/2 times 1 over 1 plus u squared, simply factoring out the 1/2. Now the 1/2 is a constant, and the integral of 1 over 1 plus u squared, you should notice it's equal to the arctangent, or the inverse tangent function. If you want to make a separate video on the derivation of that, I can show you. But simply for now, you should know that the integral of 1 over 1 plus u squared in du, is equal to the inverse tangent, and here we have a constant of 1/2. So this integral is simply equal to 1/2 of the inverse tangent of u. And u is equal to x squared, so this is going to be 1/2 of the tangent, the inverse tangent of x squared, and with our bounds from 0 to infinity. So now that we found the antiderivative of this function, the rest is quite simple, as is normal with dealing with improper integrals. Define a new variable, say t, and it's going to be greater than our lower bound, so 0. Then we know that the integral from 0 to t of this function, we just use the evaluation theorem, or part of the fundamental theorem of calculus. It's going to be the antiderivative evaluated at t minus it's evaluated at the lower bound of 0. So it's going to be half of the arctangent of t squared minus half of the arctangent of 0 squared, which is obviously just 0, so we don't need that. And then to evaluate the improper integral, we take the limit as t approaches infinity of what we evaluated here. Quite straightforward, I believe. And so the limit of half arctangent of t squared as t approaches infinity, well, think about it. The arctangent, it's the inverse of the tangent, and tangent has these asymptotes around pi over 2, right? That means as tangent is evaluated closer and closer to pi over 2, its value gets bigger and bigger. So now just apply that to the inverse. As the inverse tangent gets bigger and bigger, its value gets closer and closer to pi over 2. And the square here also doesn't affect it. That just means it'll get closer there quicker. And so the limit as the inverse tangent of some variable, for example, square 2, doesn't affect it. It's going to be pi over 2, if you remember the asymptotes from the tangent function. And here we also have a constant 1/2. So this is going to be 1/2 times pi over 2. This is what the limit evaluates to. And that is, of course, pi over 4. And this is the answer to our integral, very classic integral involving pi and the arctangent function. And that is it for today's video. Hope you all enjoyed, and I will see you in the next one.